Ethernet, it's a foundational technology that's responsible for much of the networking we use every day. Here's an introduction, covering the key aspects. 1. What is Ethernet? At its core, Ethernet is a networking standard that defines how devices connect and communicate over a local network, LAN. Think of it as the language computers and other devices use to talk to each other on your home or office network. It's the dominant standard for wired networks. 2 key concepts and history. Developed by Xerox PARC, Palo Alto Research Center, in the 1970s, Ethernet's roots trace back to research at Xerox PARC. Originally designed for Xerox machines, it was initially conceived to connect Xerox workstations together. Standardized by the IEEE, Institute of Electrical and Electronics Engineers, the IEEE developed the specifications for Ethernet, which have evolved over time. Layered architecture. OSI model. Ethernet operates at layer 2, data link layer, of the OSI model. This means it deals with framing data and addressing for physical transmission. 3. How it works. The basics. MAC address, media access control. Every Ethernet device, network card or adapter, has a unique 48-bit MAC address. This is like a device's unique ID CSMA/CD. Carrier sense multiple access with collision detection. This is the original protocol that determined how devices transmitted data. Carrier sense. Before sending data, a device listens to see if the network is busy. Multiple access. Multiple devices can try to transmit at the same time. Collision detection. If 2 devices transmit at the same time, a collision occurs. The devices stop transmitting and retry. Modern Ethernet largely eliminates collisions. Framing. Ethernet transmits data in frames, which are like packets containing the data itself and information about the source and destination. Switches. Modern networks almost exclusively use switches. A switch intelligently directs data packets to the correct destination based on the MAC address in the frame. This is much more efficient than older hubs. 4 common Ethernet types. Categories. Ethernet has evolved with different categories, each offering varying speeds and capabilities. Cat5, older, slower, up to 100 Mbps, mostly obsolete. Cat5e, improved version of Cat5, supporting 100 Mbps. Cat6, supports up to 1 Gbps, gigabit Ethernet, and can handle higher frequencies. Cat6a, enhanced Cat6, supporting 10 Gbps. Cat7 and Cat7a, even faster speeds, often used for data centers and high bandwidth applications. 5. Ethernet today, dominant wired LAN standard. Ethernet is the de facto standard for most wired local area networks. Ubiquitous in homes and offices, you'll find it in your router, your computer's network card, and many other devices. Foundation for the Internet. Ethernet is a key technology that underlies much of the Internet infrastructure. There are 2 critical layers within Ethernet, the physical layer, PHY, and the media access control, MAC, layer. These layers work together to enable your devices to communicate over an Ethernet network. 1. The physical layer, PHY. What it does. The PHY layer is responsible for the physical transmission and reception of data. It's the hardware side of Ethernet. Key functions. Signal encoding/decoding, converts digital data, bits 0 and 1, into electrical signals, voltage levels, that can be transmitted over the cable. Conversely, it converts incoming electrical signals back into digital data. Signal transmission, handles the actual sending and receiving of signals over the physical medium, example Cat5e cable. It manages things like voltage levels, defines the specific voltage levels used to represent bits. Frequency modulation, adjusts the frequency of the signal to encode data. Cable specifications, the PHY layer adheres to cable specifications, example Cat5e, Cat6, to ensure signal integrity. Clocking, provides a timing signal to synchronize the transmission and reception of data. Hardware focus, the PHY layer is primarily implemented in hardware within the Ethernet network card, NIC, or switch. Standards, the PHY layer adheres to specific standards related to cabling, example TIA/EIA 568 for cabling, and signal transmission techniques. 2. The media access control, MAC, layer. What it does. The MAC layer is responsible for controlling access to the physical medium and ensuring that data is transmitted correctly. It's the software and protocol side of Ethernet. Key functions. MAC addressing, the MAC layer assigns and uses MAC addresses, 48-bit unique identifiers, for each device on the network. This allows data to be delivered to the correct destination. Frame formatting, it encapsulates data into Ethernet frames, adding header information like source and destination MAC addresses, frame type, and error detection codes. CSMA/CD, collision detection, in older Ethernet. In older implementations, the MAC layer handled CSMA/CD. This mechanism prevented collisions by detecting when 2 devices attempted to transmit simultaneously and forcing them to retransmit. Switches largely eliminate the need for CSMA/CD now. Flow control, Helps prevent a fast sender from overwhelming a slower receiver. Software and protocol. The MAC layer is implemented in software within the NIC or switch. Frame structure. It defines the structure of Ethernet frames, which includes preamble, a sequence of bits used for synchronization. Frame header contains the source and destination MAC addresses and other control information. Data field contains the actual data being transmitted. Frame check sequence, FCS, an error detection code used to verify the integrity of the data. How they work together. 1. Data originates. Data is generated on one device. 2. MAC layer encapsulation. The MAC layer adds a header to the data, creating an Ethernet frame. 3. PHY layer transmission. The PHY layer converts this frame into electrical signals and transmits them over the cable. 4. Reception. The PHY layer receives the electrical signals. 5. PHY layer decoding. The PHY layer converts the signals back into digital data. 6. MAC layer processing. The MAC layer processes the frame, checks the FCS, and delivers the data to the correct destination. The logical link control, LLC, layer is the upper sublayer of the data link layer, layer 2, in the OSI model, defined by the IEEE 802.2 standard. It acts as a crucial interface between the network layer, layer 3, software, and the media access control, MAC, sublayer hardware, providing a uniform way for various network protocols, like IP, IPX, to operate over different physical network technologies, including Ethernet. Role of LLC in Ethernet protocol multiplexing. The primary function of LLC in modern Ethernet is protocol identification and multiplexing. It uses service access points, SAPs, in its header to specify which network layer protocol, example IP, ARP, the encapsulated data belongs to, allowing multiple protocols to share the same physical link simultaneously. Abstraction. The LLC layer provides a consistent interface to upper layers, shielding them from the specific details of the underlying MAC and physical layers, example whether it's standard Ethernet, token ring, or Wi-Fi. Error and flow control. Historically/optionally, while modern wired Ethernet primarily relies on higher layer protocols, like TCP, for reliable end-to-end communication, the LLC standard, IEEE 802.2, defines optional services for flow control, sequencing, and error recovery at the data link layer, example Type 2 connection-oriented service. This is more common in wireless networks, IEEE 802.11, or legacy systems. LLC in modern Ethernet frames. Modern Ethernet predominantly uses the simpler Ethernet 2 frame format, which includes a type field to identify the upper layer protocol, bypassing the need for a full LLC header in most TCP/IP implementations. However, the LLC sublayer is still used in IEEE 802.3 compliant frames, often with the Subnetwork Access Protocol, SNAP, extension. In these frames, the LLC header contains specific fixed values, DSAP equals AA hex, SSAP equals AA hex, that indicate the presence of a SNAP header, which in turn holds the type field to identify the network protocol. This ensures compatibility across different IEEE 802 standards. Jumbo frames are Ethernet frames with a payload size, maximum transmission unit, or MTU, greater than the standard maximum of 1,500 bytes. While not part of the official IEEE 802.3 standard, they are widely adopted in high-speed local area networks, LANs, especially in data centers and storage area networks, SANs, to improve data transfer efficiency. Standard versus jumbo frames. Features. Standard Ethernet frame. Jumbo frame MTU, payload commonly 9,000 bytes, ranges from 1,500 up to 1,500 byte size, 65,535 bytes, 1,518 or 1,522 bytes, with total frame size varies by vendor implementation. VLAN tag, efficiency. Higher overhead to data ratio, lower overhead to data ratio. How they work and their benefits. The main purpose of using jumbo frames is to improve the efficiency of data transfer for data-intensive applications. Reduced protocol overhead. Each frame requires a fixed amount of header and trailer information, example source/destination MAC addresses, IP info. By sending more data in a single, larger frame, the relative amount of overhead is reduced. For example, a single 9,000 byte frame can replace 6 standard 1,500 byte frames, eliminating 5 sets of headers. Lower CPU utilization. Fewer frames to process means fewer network interrupts and less work for the CPU on both the sending and receiving devices. This frees up CPU cycles for other tasks, improving overall system performance. Increased throughput. The network can move more actual data per unit of time, which accelerates large file transfers, data backups, and video streaming applications. Considerations for implementation. For jumbo frames to work correctly, every device in the entire layer 2 network path, network interface cards, switches, routers, must be configured to support the same maximum frame size. Configuration mismatch. If a device configured for jumbo frame sends an oversized packet to a device that expects a standard frame size, the packet will either be fragmented into smaller pieces, which negates the benefits, or simply dropped, leading to performance issues and potential connection breaks. Best use cases: jumbo frames are most beneficial in dedicated, high-speed, controlled environments like SENS or high-performance computing, HPC, clusters, where large amounts of data are consistently moved between servers and storage devices. They are generally not recommended for typical office or home networks, and devices connecting to the public internet must adhere to the standard MTU of 1500 bytes.